Welcome back. If you're new, let me start by saying welcome. This isn't some polished studio show. This is a workbench, a place where we break issues down, solve problems, argue the math, and get shit done. To my returning design junkies, know this. You are shaping something greater than yourself. Every cut, every correction, every failure becomes part of the person you carry into tomorrow. The universe remembers the workers, not the watchers. So show up, endure, and build. And get ready for the deep dive into infrastructure design. Today, we are taking a deep dive into the dense, fascinating, and just critically important world of civil and environmental engineering practice.
There really is. When you think about infrastructure, I mean, the bridge you drive on, the water from your tap.
Right, the power grid, all of it.
Yeah.
These are projects that define societies for decades, sometimes even centuries.
And the complexity, well, it's astronomical. The challenge now goes so far beyond just making sure it doesn't fall down.
Exactly. The modern engineer, you have to prove the financial viability, you have to establish the ethical framework, and you have to ensure the long-term environmental worth of a massive blueprint. It's a huge undertaking. So our sources today are going to give you the complete toolkit for this practice. We're synthesizing everything. We'll start with the foundational principles, so professional ethics, communication standards.
And then we get into the cold, hard math.
Yes, the cold calculus of net present value, life cycle costing, and then we'll land on this really cutting-edge ethical framework for sustainability assessment.
And to make it all stick, we're grounding it in a real-world case study.
The Orange County Groundwater Replenishment System, a project that is, it's both a technical marvel and a really profound ethical challenge.
It really is.
So our mission today is to give you the shortcut, the inside track to understanding the multifaceted demands of designing and financing a world that can actually last.
That holistic view is, it's absolutely essential now. We are talking about projects that fundamentally alter the landscape. They determine who gets resources, for entire populations.
And you really need to grasp the history here, the context of modern CE consulting.
Right. A lot of the big specialized firms you see today, the ones that are really focused on environmental impact, they weren't just founded because of technical expansion.
No, it was a reaction, a direct response to legislation.
Exactly. Specifically, major environmental laws like the National Environmental Policy Act, NEPA, and the California Environmental Quality Act, CEQA. Both of those popped up right around 1970.
And that moment just completely changed the game, didn't it? It forced a radical change in the organizational chart.
It did. It demanded that these massive infrastructure projects had to consider their secondary and tertiary impacts before a single shovel ever hit the dirt.
A huge shift in accountability.
A massive societal need for it. The mission of these specialized firms today, it's explicitly stated as providing scientifically accurate, innovative, and practical solutions to environmental challenges.
Which means the old engineering silo had to go.
It had to shatter.
Okay.
You can't just rely on a civil engineer and a draftsman anymore. Not for these projects.
So who do you need in the room?
To manage a complex environmental impact statement, or to design a system like a regional water plan, you need a true coalition of experts. You need biologists looking at wetlands, planners dealing with zoning.
Economists, I'm guessing, to model out the future costs.
Oh, absolutely. Economists, specialized environmental engineers, attorneys to navigate the permitting labyrinth, and information technologists managing all the data. The sheer variety of expertise required today, it just reflects the magnitude of the problems we're trying to solve.
Problems that, let's be honest, our forefathers created when the only metric for success was just, well, immediate progress. Okay, so let's unpack this. Before we even touch the math or the technical schematics, we have to start with the cornerstones of the profession. That's ethics and communication. And these aren't just, soft skills. They are foundational tools that protect the public and the engineer from catastrophic failure, whether that's physical or legal.
The ethical framework is the absolute bedrock. It has to be, particularly because CE work almost always involves public funds, public safety, and, crucially, public trust.
And the American Society of Civil Engineers, the ASCE, they lay this all out.
They do. They have fundamental canons that serve as the guide, the North Star, for every single engineer.
And the sources are really clear on this. The very first of these canons is the most critical, the most non-negotiable principle.
Which is the mandate to hold paramount public safety, health, and welfare.
That's the starting line.
It is. It sets the standard that everything else cost, schedule, what the client wants, all of it is secondary to protecting people.
But that definition of public welfare it's grown, hasn't it? It's matured.
It has. In the modern era, the ASCE explicitly added the requirement that engineers must strive to comply with the principles of sustainable development.
And that's huge. That's where the profession moves beyond just building a structurally sound object.
To ensuring that the object doesn't compromise the long-term health of the environment or, future societal stability. It's a massive expansion of responsibility.
It turns the engineer from just a technical problem solver into a steward of generational resources.
Precisely. And beyond that main mandate, you have other key principles that reinforce integrity. Engineers have to use their knowledge only for human welfare, be honest and impartial.
Serve with fidelity. I like that phrase.
Right. Serve their employers and clients with fidelity and this is crucial, continually increase their competence.
So you can't just rest on your laurels.
No, that last point about competence is not passive. It is an active responsibility. You have to engage with new technologies, new materials, and new ethical challenges. The National Institute of Engineering Ethics, their NIEE, they talk about this.
What's their take?
They point out that ethical decision-making isn't just a theory problem. It has to lead to practical solutions to gut-wrenching circumstances you run into in professional life.
Gut-wrenching circumstances. That sounds about right.
Well, think about it. The easiest choice, especially when you're under financial pressure, is often the ethically questionable one. The integrity of the engineer is truly tested when projects go sideways, when deadlines are screaming, or when safety gets questioned.
So if you're faced with a tough choice, say a contractor is cutting corners on the material spec, the mandate isn't just to say no.
Correct. It's about finding a compliant and practical solution that protects the public. It demands proactive intervention.
And clear communication, which I guess transitions us perfectly into the next major tool in the toolkit.
It does. Because if you make the right ethical call but you fail to document it or articulate it clearly, you've put yourself, your firm, and the public at risk.
We often think technical competence is just about, the calculations and the design work, but our source material is adamant on this point.
It is.
Technical writing and oral presentation skills are at least as important as technical competence itself. Why is that?
Because your communication is a direct reflection of your clarity of thought. It's that simple. If your report is ambiguous or confusing or just poorly structured, people will question your technical judgment.
A sloppy report implies sloppy engineering.
That's it, exactly. For an engineer, being able to articulate a complex design or a financial justification or an ethical dilemma, it's fundamental to getting the project approved and making it a success.
And you have to be so aware of your audience.
Acutely aware. The style, the level of detail, the formality, it all has to adjust significantly based on who is reading your work.
Give us an example.
Okay, a report for your fellow structural engineers. You can use all the high-level jargon and formulas you want, but a presentation to the city council that holds the purse strings.
You better focus on community impact and the cost-benefit numbers.
Right. And a document for a permitting bureaucrat needs meticulous adherence to regulatory language. And then if your communication is headed for a court of law,
the tone shifts completely. It's just strict factual impartiality.
That anticipation of the ultimate audience is the absolute key, especially now in the digital age. We have to talk about email. A single, off-the-cuff email can suddenly become Exhibit A in a lawsuit worth millions.
It's a professional landmine.
It is.
Yeah.
Every engineer must treat every communication as a formal record. The rule is simple. The tone is always professional. No slang, avoid jokes, and for God's sakes, review your messages carefully before you hit send.
And you definitely should not be conveying bad news via email.
Absolutely not. A major project delay, a safety breach that needs a phone call or a meeting. It needs human context. Email is the worst possible medium for that.
What about that cardinal sin, responding in a panic?
Never, ever panic and take responsibility in a hasty email. You need to gather the facts, consult legal counsel if you need to, and then formulate a careful professional response.
The sources have a great test for this.
We do. Picture your words enlarged on poster board before a jury test.
It's a brilliant mental filter. Just imagine every single word you type, maybe in a moment of anger, blown up in huge font in front of a court with a lawyer picking it apart.
That image immediately removes any ambiguity or flippant language. It forces you to be precise. And you have to assume that a deleted email is never really gone.
Right. Digital forensics can find anything.
So maintaining high standards for prose and clarity is just. It's non-negotiable. For a big document, outline it first. A well-structured document shows you have a well-structured plan. Use strong topic sentences. Get to the point. And maybe most importantly, use parsimony. Less is more. Short, declarative sentences. You want the relationship between the subject and the verb to be immediate and unambiguous. No room for misinterpretation.
Okay, so we've got the ethical and communication frameworks in place. Now we need to shift to the business strategy behind the engineering firm itself.
Right, because projects don't just happen. They need to be sold, and they need to be executed profitably. This starts with defining the firm's business idea.
The business idea. What is that exactly?
It's basically the organization's big picture mental model for how it's going to succeed financially and create a surplus for its stakeholders. It covers how the firm sees the market, what its core strengths are, and its strategy for growth.
Oh.
Without a clear one, a firm just flounders.
And when you look at gaining a competitive advantage in the engineering and construction sector, the E&C sector, our sources point to two very different paths.
Starkly different. Path 1 is offering a differentiated product. This is the strategy that commands a premium price.
How do you do that?
You have to deeply understand what your customers really, truly value. And that might be speed or complexity management or navigating politics or superior sustainability. And then you deliver unique, unmatched services that others can't easily copy. It requires a heavy investment in specialized talent.
And the other path is the complete opposite.
Path 2 is becoming the low-cost commodity provider. This means achieving absolute cost leadership on a standardized product. Think of firms bidding on basic road grading, where the design is generic. The competitive edge there is just ruthless efficiency.
The sources seem to suggest that the future, especially for these huge, complex infrastructure projects, requires a move away from that low-cost model.
It does. It suggests a move toward a much more sophisticated model. The master builder of the 21st century.
Okay, what does that look like?
The master builder model is all about those premium, differentiated services, but they're achieved through deep vertical integration.
So the HUM doesn't just design or just construct.
No, they integrate the whole process. Strategy planning, concept development, detailed design, construction, and even long-term operations and maintenance, or O&M, all under one roof.
How does that vertical integration affect the risk and, more importantly, the profit margin for the firm?
It's a fundamental change. When you move from just being a designer, which is low risk, low margin, or just a builder, which is high risk, moderate margin, toward this integrated model, your liability goes way up.
Because you're responsible for the whole thing.
The entire outcome. But your potential margin also increases dramatically, and you get superior control over the schedule, the quality, the cost. The thing that justifies the premium price for this model is superior systems engineering capabilities.
The ability to manage complexity across the whole life cycle.
Exactly. Making sure that long-term O&M costs are minimized because you did a superior job on the upfront design and construction.
That integrated approach brings us perfectly into the life cycle of a project itself. If you're managing the whole thing, you have to understand every single stage.
From the first sketch to the final demolition order, and who is responsible for what at each point.
So a major infrastructure project has this long arc. What are the key stages?
It begins with conceptual planning and feasibility studies, establishing the need and if it's even viable. Then it moves into detailed design and engineering where the blueprints get finalized.
When the dirt starts moving.
Right. Procurement and construction, the physical build. That's followed by startup and commissioning. Then comes the longest phase, which can be decades.
Operation and maintenance, O&M.
Exactly. And finally, the project concludes with renovation, conversion, or demolition.
Understanding those phases is one thing, but what's even more critical for risk and liability is differentiating the main roles, the architect-engineer versus the contractor.
Oh, the lines of responsibility there have to be crystal clear.
So the architect-engineer, the AE, what's their fundamental role?
They are the owner's representative, period.
Yeah.
Their duties are, well, they're numerous. They administer the contract for the owner, they advise the owner, and they often act as the judge of performance and the arbiter of disputes between the owner and the contractor.
And their primary responsibility.
The quality and correctness of the design, that's on them. They have to visit the site periodically to get familiar with the progress and the quality of the work.
But the sources stress a really crucial distinction here about what happens on the site. What is the AE specifically not responsible for?
The AE is absolutely not responsible for the contractor's construction methods. How they actually choose to pour the concrete or lift the steel.
And maybe surprisingly, to people outside the industry, they're not responsible for site safety either.
Not at all. That liability rests entirely elsewhere.
And that elsewhere is the contractor. Their role is completely different.
Completely. The contractor supervises all the construction work, provides a full-time superintendent on site, and make sure they stick to the schedule and plans. They take full responsibility for the means and methods.
And they also have a critical legal obligation to the owner.
Yes, the contractor typically has to indemnify the owner against any third-party claims from their work or safety failures. If someone gets hurt on that job site, the legal liability is squarely with the contractor, not the design firm. Assuming, of course, that the plans themselves were correct.
Okay, so once the design is set and the roles are defined, the project has to pass the ultimate test. Is it financially feasible?
Hmm.
And this brings us to the absolute foundation of project evaluation: net present value, or NPV.
NPV is the crucial tool. It's what project managers, what investors use to determine if a project's future cash benefits are greater than its costs, and specifically relative to other investment opportunities.
So it answers the question, is this the best use of my money right now?
That's the fundamental question. Is this project a better use of capital than something else I could invest in? We're trying to solve for the current value, the present worth of all the future cash flows from the project.
Because money today is worth more than the same amount of money tomorrow.
Right. Because the money you have today can be invested to earn a return. That lost opportunity to invest is the opportunity cost of capital. So NPV calculates the present value of every single future net benefit and then sums them all up.
Let's break down the formula, especially the denominator. That's the part that can be tricky.
Absolutely. The core idea is you take the future net benefits for a specific year, so the project's income minus its expenses for that year, and you divide that amount by the quantity 1 plus the discount rate, all raised to the power of the number of years into the future.
So mathematically speaking,
Right. The present worth of a cash flow in year n is equal to the net benefit in year n, divided by the quantity 1 plus I raised to the power of n, where I is that discount rate.
and it's that denominator, that quantity 1 plus I to the power of n, that really crushes the value of long-term benefits or costs.
It's the engine of financial time travel. It truly is. If you expect a net benefit of, say, 1 million in 20 years, and the market demand a 10% discount rate, the present value of that million is, it's significantly less than a million.
The formula is basically asking, how much money would I have to invest today at rate I to end up with that future amount?
Exactly. And if the sum of all those discounted values, the total NPV, is positive, then the project is financially viable. It means it's theoretically yielding a higher return than the alternative investment represented by that rate.
And that discount rate, that's where all the market's perception of risk and inflation gets bundled together.
It is the most subjective and powerful variable in the whole model. It's not a single number. It's composed of 3 critical factors. The risk-free rate, which is the base return you could get on something super safe like government bonds.
A risk premium.
A risk premium, which reflects the specific project's risk, and an inflation premium, an NF, which accounts for the loss of purchasing power over time.
You can see this dynamic of risk versus return plotted out clearly across the whole investment market.
Oh yeah, if you look at asset classes, there's a direct correlation. Government bonds are at the bottom, lowest risk, lowest expected return. As you move up the curve, you get into corporate bonds, stocks, and then, things like emerging market stocks.
Which carry the highest perceived risk.
Highest risk, and so they demand the highest expected returns to attract any capital.
So here is the crucial insight for you as a developer or an engineer trying to get a project funded. Reducing the perceived risk of your project allows you to raise more money today.
That is the ultimate financial leverage point. If your project, let's say it's a new toll road, is seen as highly risky, investors will insist on a high discount rate, maybe 15%. And that shrinks the NPV of your future toll revenues.
If you can minimize that risk.
If you can provide contractual guarantees, secure your permits, show strong political support, you minimize that risk premium. Investors might then accept an 8% discount rate, and that substantially increases the calculated present worth of the project, making it much easier to raise the capital you need right now.
Lower perceived risk means a higher NPV.
And a much more viable project today.
Let's ground this with the skyscraper example from our sources. It really highlights how different players handle risk through leveraging.
The skyscraper scenario is perfect. It shows how project finance uses different banks for different risk phases. You've got 3 players, Bank 1, Bank 2, and the owner-developer.
Okay, so Bank 1 provides the construction loan. This covers all the costs for the 3 to 5 years of building. Why does this loan have such a high interest rate?
Because the risk is enormous. During construction, the project is just this massive financial liability. It's a hole in the ground with uncertain completion and no tenants yet. If the developer defaults, Bank One is stuck with an incomplete building that's almost impossible to sell.
So they're assuming all the execution risk.
All of it. So they demand a high interest rate, maybe the prime rate, plus several points.
But Bank One is only involved for the short term.
Right. Once the building is gone and tenants are secured, they get paid off. And that's when Bank Two steps in with the permanent mortgage.
And Bank Two's risk profile is totally different.
Night and day. Their financing is stabilized asset. It is secured contractual revenue streams from tenants paying rent. The feasibility is proven, the structure is sound, the cash flow is predictable. So Bank Two applies a much lower discount rate. The mortgage has a significantly lower interest rate and provides that long-term annuity structure.
And the owner-developer strategy is just pure leveraging.
Pure leveraging. They borrow Bank One's expensive money to build. Then they use Bank Two's cheaper permanent financing to pay off Bank One immediately. After that, the owner-developer just focuses on making sure the rent checks cover the mortgage payments to Bank Two with plenty left over.
So the key takeaway is that the capital structure is dictated by risk.
100%. Project finance is all about segmenting and shifting risk over the life cycle to minimize the overall cost of capital.
That discussion leads us right into a deeper look at cost modeling. For infrastructure that lasts decades, the initial price tag is just one small piece of the pie.
Right. The true cost is the total life cycle cost, or LCC.
The initial cost can be so misleading.
Almost always. The structure might be cheap to build, but ruinously expensive to maintain or repair or replace. LCC captures that whole cumulative financial burden across the entire lifespan.
And you can calculate this in a couple of ways.
Right, either as the net present value of all those future costs, or as the equivalent uniform annual cost EUAC, which kind of smooths everything out into a single average annual payment.
And the LCC model forces the engineer to look decades ahead. We have a list of 10 critical cost elements that have to be factored in.
And it's a comprehensive list. It starts with the obvious stuff: purchase of materials, transport to the factory, and production. Then you move to the site, transport to the site, and construction.
But the real long-term costs start kicking in after the ribbon cutting.
That's where the ongoing financial burden really lives. You've got inspection costs, maintenance costs for routine upkeep, and then rehabilitation costs for major overhauls like resurfacing a road.
Then replacement costs.
For when the component just reaches the end of its life. And finally, the most volatile and potentially catastrophic cost of all:
Failure costs.
failure costs. The financial impact of the system failing prematurely. This includes emergency repairs, downtime, lost revenue, environmental cleanup, litigation, and in the worst case, the cost associated with loss of life. These costs can be many, many multiples of the initial component cost.
So what drives the cost of the components themselves? How do those cost drivers shift?
It depends entirely on availability and complexity. For something cheap and widely available like gravel for a roadbed, the material cost itself is low.
So transportation is the big expense.
Exactly. Transportation costs dominate the LCC calculation. Getting all that bulk material from the quarry to the site is the major expense.
And on the other end of the spectrum,
If you're buying specialized items like high-strength, corrosion-resistant steel, or, Italian marble for a big project, the material quality and the specialized labor for fabrication and installation, that dominates the cost. Transport becomes a much smaller piece of the pie.
this detailed cost breakdown leads us to the core trade-off in CE design: initial cost versus long-term durability.
Right. The engineer has to choose materials that balance those two forces to minimize the overall EUAC. The whole project is a hierarchy. You have the system, like a rail network. That system is made of elements, like a mile of track, and those elements are built from components.
The rails, the concrete ties, the fasteners.
All of it. And every single component choice reflects a direct trade-off. Do we use high-grade, expensive steel for the rail that lasts 50 years with minimal repair, or cheaper steel that needs replacing every 25?
And this is where R&D and materials science, like using composite materials instead of traditional steel, gets justified.
Totally. The composites might have a higher purchase price, but they are dramatically lighter. So you get massive savings in transport and, most significantly, in installation costs and labor. Plus, they often need less maintenance because they don't corrode. If you run the EUAC calculation, that initial premium is paid back very quickly.
This brings us back to risk management and inspection. The frequency of inspection is directly tied to the risk of failure.
It's a fundamental engineering decision based on what level of risk is acceptable. If a component failure is a minor inconvenience, inspection might be minimal. But when the consequences are catastrophic loss of life, huge economic disruption, the inspection interval has to shrink dramatically.
Like with a high-speed rail network.
A perfect example. The track components are under extreme stress. Failure isn't an inconvenience, it's a mass casualty event. So the sources confirm that high-speed lines require ultrasonic testing and inspection intervals that are sometimes daily
Daily.
or near daily. The cost of that hypervigilance is a massive operational cost, but it's necessary to reduce the probability of catastrophic failure costs to an acceptable minimum. The more a thing gets used, the more it pays to invest in better, high initial cost components up front.
So the cheap solution is usually the most expensive solution over the long haul.
Almost always. An engineer's real competence lies in justifying that material quality over a 100-year timeline.
So we've established the technical, ethical, and financial frameworks. Now we hit the core modern dilemma. How do we make sure that financially viable projects are also environmentally and socially responsible?
And history gives us a stark illustration of this shift.
We think of engineering figures like William Mulholland, who built the Los Angeles Aqueduct, as this engineering hero, a symbol of progress.
And he was, in that paradigm. But that narrative gets challenged when you view it through an environmental and ethical lens. The quote from Cadillac Desert just captures the systemic problem of unchecked growth perfectly.
Remind us of that quote.
This is a desert. Why bring more water in that brings in more growth, that forces us to bring in more water? It's a death vortex, the Red Queen running faster and faster just to stay in place.
That tension progress versus sustainable limits is exactly why traditional cost-benefit analysis, or CBA, is just not enough anymore.
It's great for balancing a ledger today, but its major flaw is its systematic inability to adequately value externalities.
The costs that aren't on the project's immediate balance sheet.
Exactly. CBA really struggles to put a price tag on social well-being, on ecological services, on environmental preservation. And because it relies on discounting, it systematically downgrades the importance of the future.
Meaning a cost 100 years from now, like cleaning up a polluted watershed, is treated as almost worthless in today's calculation. It just ignores generational equity.
Precisely. To fix this failure, the concept of sustainable development became paramount. The widely accepted Brundtland definition from 1987 is the ethical compass,
Which is?
meeting present needs without compromising the ability of future generations to meet their own needs. This requires assessing the triple bottom line: economy, society, and environment.
And since traditional CBA can't do that well, we need new methods.
We do, and our sources highlight a really elegant framework: the 7 questions to sustainability.
And what's the methodology here? Is this like a scoring system?
No, it's what's called a soft systems approach.
Sure.
It's not designed to give you a single number or rank things. The goal is to use 7 key themes to ensure the project gets rigorous, systematic scrutiny, and is fundamentally compatible with sustainability concepts before it gets the green light. It's an essential due diligence checklist for stewardship.
Let's walk through these 7 questions. They seem like a great structure for assessing any big project. What's number 1?
Question 1 is engagement. Are stakeholders involved effectively? Is there informed consent? And this is way more than just one public meeting.
It's about ongoing communication.
And dispute resolution. And, crucially, it forces you to define stakeholder expansively. It includes organized labor, indigenous communities, NGOs, and it explicitly recognizes the interests of future generations who can't speak for themselves.
Okay, question 2. People. Will people's well-being be maintained or improved?
This is the socioeconomic dimension. It's about measuring health, safety, community vitality. It requires a full socioeconomic impact assessment. You have to consider the trade-offs.
Like a big construction project brings jobs, which is good, but it also strains the local housing market.
Exactly. A responsible assessment has to show how you'll mitigate those short-term stresses.
Question 3 is environment. Is the long-term integrity of the environment assured?
This is a direct challenge to that old Mulholland mindset. It requires rigorous assessment of biodiversity, water quality, air quality, and it means ensuring that your resource extraction rates do not exceed your renewal rates. That's often the hardest principle to satisfy.
Question 4, economy. Is the project financially viable, and will the broader economy benefit?
Right, so it has to have a positive NPV for the owners, but it also has to demonstrably improve the local or regional economy. Does it create new industries? Does it make the area more competitive?
Question 5 covers traditional and non-market activities. This is the stuff that CBA usually ignores.
And it's a vital correction. It asks whether cultural practices, indigenous rights, or local recreational activities are accounted for and protected. For example, if your project affects a popular fishing spot, you have to assess that impact and maybe provide an alternative. It mandates respect for these non-monetary human activities.
Number 6, institutional arrangements and governance.
Are the laws and the government bodies capable of managing the project's consequences over its entire lifespan? Infrastructure creates permanent burdens. This question makes sure the institutions can cope. Are the monitoring programs funded? Is the entity in charge stable enough to last 50 years?
And the final question, number 7, is the overall integrated assessment and continuous learning.
Yeah, it forces a holistic review. Considering everything, will the net result be positive in the short and long term? And just as importantly, are there transparent mechanisms for reassessment and continuous learning built into the project's governance? Sustainability isn't static, it's a dynamic process.
Let's apply this framework to a real-world project. The Orange County Groundwater Replenishment, or GWR, system in Southern California. This was born out of profound necessity.
It was. The context is a severe and deepening water deficit crisis. Southern California has explosive population growth, and at the same time, their imported water supply from the State Water Project and the Colorado River is shrinking.
The Colorado has been overallocated for decades.
Chronically. And climate change is just making it worse. Orange County desperately needed a local, reliable water supply.
So the technical solution they came up with, the GWR system, is a marvel of purification technology. Walk us through that process.
The system takes treated wastewater, water that would otherwise just be dumped in the ocean, and turns it into water clean enough to drink. It's a three-stage process. Stage 1 is microfiltration.
Using superfine hollow fibers to strain everything out.
Right. It pulls out solids, bacteria, protozoa. Then you move to stage 2, the centerpiece, which is reverse osmosis, RO.
This is where you force the water through a membrane at high pressure.
Yes, and it removes dissolved salts, viruses, pesticides, even pharmaceuticals. The water that comes out is cleaner than the requirements for bottled water.
And the final barrier.
Stage 3 is UV disinfection with hydrogen peroxide, which just obliterates any residual organic molecules. The result is ultra-pure water that then gets injected back into the groundwater basin, replenishing the aquifer.
So if we evaluate GWR with our 7 questions framework, it checks a lot of positive sustainability boxes.
It does. On the economy question, the total project cost, about $481 million, was partly offset by avoiding the construction of a new ocean outfall, which saved an estimated $170 million. And it provides a highly reliable, locally controlled water source.
What about engagement and people?
Public support was extraordinary, something like 87% of voters. And the benefits are tangible. The GWR water is softer, so it reduces scaling in pipes and appliances, saving consumers money. And it improves the long-term quality of the groundwater basin itself.
And environmentally, it's a huge win over the alternative.
Absolutely. The system uses about 50% less energy than pumping imported water from hundreds of miles away. Plus, it creates a hydraulic barrier against seawater intrusion, protecting the existing groundwater from being ruined by salt. One director even compared it to the LA aqueduct, saying future generations will see it as visionary.
Okay, so despite all these clear benefits and the technical brilliance, the sources highlight a profound and critical sustainability gap. What is the ultimate flaw of the GWR system when you hold it up to that highest standard of generational equity?
The core limitation is that the Environmental Impact Report, the EIR, it didn't, and maybe couldn't, address the fundamental problem of groundwater overdraft.
So it treats the symptom, not the disease.
That's a perfect way to put it. The GWR project is an impressive technical fix for a crisis, but it fails to address the underlying issue of unsustainable extraction rates.
Let's get into the math on that. What are the numbers for sustainable yield versus what they're actually planning to use?
The safe yield, the amount of water that's naturally and artificially recharged, which should be the absolute limit of what you take out, is estimated at 274,000 acre-feet per year.
Okay, but the projected demand?
The projected demand is 450,000 acre-feet per year. So they intend to extract 176,000 acre-feet more than is replenished every single year.
So even with the GWR system putting 120,000 acre-feet back in, they are still deep in the red.
Correct. The core principle of sustainable development for any resource is that the rate of extraction should not exceed the rate of renewal. The GWR system slows down the deficit spending, but it still violates that principle.
And this can't go on forever. What are the long-term consequences?
The source material is very clear. It leads to lower well yields, chronic water quality degradation, and the most physically devastating one, land subsidence. The land literally sinks as the underlying water is drawn out and the soil structure collapses. The conventional financial assessment, by focusing on immediate savings, completely misses this fundamental failure.
This transition from the drawing board through the financial justification and into this ethical assessment brings us to the professional edge itself. How do engineers position themselves to manage these huge projects and communicate their value?
Right, we're moving from the technical back to professional competence in the marketplace. Whether you're applying to a firm managing GWR or designing the next big bridge, the key takeaway from recruiters is the 10-second rule.
Your resume and your first impression have to communicate competence and value fast.
Clearly and quickly.
And what are these big E&C firms actually looking for? It's not just the GPA, is it?
It's often not. It's the human element. They look for strong people skills, demonstrated common sense, a good personality group fit. One senior officer called it the glass of beer test.
Would I enjoy having a beer with this person after a long day?
Exactly. And demonstrable enthusiasm. Headhunters often estimate that 70% of the hiring decision comes down to chemistry and personality.
And they are specifically looking for candidates who are seller doers. Explain what that means.
A doer is a highly competent technical person who does the work but can't really bring in new business. A seller is great with clients, but maybe lacks the deep technical skills. A seller doer is the ideal.
The person who can do both.
Right. The person who can successfully manage and execute complex technical projects while also cultivating client relationships and bringing in repeat business. That's the fast track for career advancement.
So in a competitive market, those small advantages in the interview are decisive. What's the best advice for nailing it?
Preparation is absolutely non-negotiable. You have to research the employer, know their recent projects, their reputation. During the interview, you have to project confidence, be relaxed, be articulate, show genuine enthusiasm for their work.
And what about the common mistakes that get people disqualified immediately?
The simple professionalism stuff that people forget. Attire. Always default to conservative business attire. You can't be overdressed. Body language, firm handshake, sustained eye contact, punctuality. Arrive 10 to 15 minutes early.
Keep your answers concise.
2 to 3 minutes, max. And for the love of all that's professional, turn off your cell phone. Put it away. A ringing phone in an interview is just immediate disrespect.
And when you get those behavioral questions, the tell me about a time when questions, the standard approach is the STAR method.
STAR. It stands for situation, task, action, and result. It's a structured way to articulate your past accomplishments without rambling.
Can you walk us through a quick example? Say, for a question about handling criticism.
Sure. The interviewer asks, tell me about a time your technical judgment was challenged. You use STAR first, situation S. During a final design review, the contractor challenged our soil-bearing calculation, saying it would add millions to the foundation cost.
Okay, then task T.
My responsibility was to ensure the foundation was safe while also minimizing cost. Then, action A. I didn't dismiss them. I immediately pulled our data, met with their engineer, and we compared our models side by side.
And finally, the result.
We agreed their approach was too risky. But based on our discussion, I identified a different, still compliant design that saved the client $1.2 million without compromising safety. It actually strengthened my relationship with the contractor. That's the kind of structured, quantifiable answer hiring managers want to hear.
We have to address this lingering stereotype that the sources highlight, that engineers are often too theoretical or lack a basic understanding of business and finance.
It's a major hurdle for technical people who want leadership roles. If you can't speak the language of finance, you'll be confined to technical work, while the people who understand NPV and cash flow make the strategic decisions.
So how do you overcome that stereotype and show you have business savvy?
You have to show practical applications of your knowledge to business problems right there in the interview. You might not have an MBA, but you can show you understand your previous employer's cost structures or the market risks on a project you worked on. If you've done any private investing, or if you have a startup mentality, even if it failed, that shows an entrepreneurial drive. The goal is to prove you understand that every technical decision, from choosing steel over composites to setting an inspection schedule, has a quantifiable financial implication. You're not just a doer of physics, you're a manager of risk and capital.
Wow, we have covered a huge amount of territory today. From the ethical canons that protect public health, through the rigorous math of net present value and life cycle costing, and then analyzing a massive real-world water project through the lens of sustainability.
And the core lesson, it really ties all these threads together. A truly successful project, whether it's a skyscraper or a complex water system like the one in Orange County, it requires this perfect active alignment between ethical frameworks, rigorous financial modeling, and deep technical competence.
So the engineer's role is not just to calculate that present worth equation.
No, it's not just about calculating that future net benefit divided by the quantity 1 plus I raised to the power of n. It's about ensuring that every single decision explicitly aligns with the non-negotiable principles of sustainable development and generational equity.
Here's where it gets really interesting. We saw that the financial viability of the Orange County GWR system, like almost all major infrastructure, is calculated using market-driven discount rates. These rates, by design, inherently apply lower and lower value to costs and benefits the further out you go in time. If a cost is incurred 100 years from now, like land subsidence or ecosystem failure due to chronic overdraft, traditional NPV calculations treat it as virtually worthless. So the ultimate moral math problem is this. How can the engineering profession mandate generational equity, a principle that should be priceless and non-negotiable, if the required financial model forces that future value to be treated as negligible? What new financial instruments or assessment tools must we adopt to truly account for the principle of sustainable yield, ensuring our balance sheets reflect the catastrophic, long-term cost of environmental negligence? That's it for today, Design Junkies. If you're getting something out of this, follow the podcast and leave a review. It helps the whole family grow, learn, and build better together. A family that solves together stays together.